In this lesson, we are going to talk about exponential models. So these are real-world applications of using exponential functions. Places that you see exponential models include bacterial growth or population growth. We also see it for radioactive decay, and we see it in interest problems. So for our first example, let's say that we are told that the temperature of an object in degrees Fahrenheit after T minutes is represented by the equation T of T. So capital T is the temperature at little t, which is the time, is given by the expression 68 times e to the negative 0.0174 t plus 72. What is the temperature after 1.5 hours? So the first thing that we need to do is convert 1.5 hours to minutes. 1.5 hours is the same thing as 90 minutes. And the temperature at 90 minutes, everywhere we see a little t, we're going to put a 90. So in order of operations, we're going to first take the product, negative 0.0174 times 90, and then use that as the exponent, e raised to that power, multiply by 68, and then add 72, and we end up finding that the temperature at 90 minutes is going to be 86.2 degrees. In general, if I think about the graph of this function, it has been shifted up 72 degrees. So that is my horizontal asymptote. The exponent, e to a negative power, means that it has been flipped over the y-axis, a horizontal flip, which makes it a decreasing function. At time equals 0, the temperature of this object would be 68 plus 72, or 140 degrees, and that would be my y-intercept, which not drawn to scale. And our question wanted to know what was the temperature at 90 minutes, and that is the 86.2 degrees. So moving on, doing another example. This is talking about radioactive decay. The half-life of carbon-14 is 5,730 years. How much of the initial amount of carbon-14 is present after 10,000 years? So, exponential decay is modeled by the function a equals a sub 0 e to the kt. A is the current amount at time t, the amount at time t. A sub 0 is the initial amount. And k is some constant that tells us how the carbon-14 is decaying, and t is the number of years. So half-life is the amount of time needed for carbon-14 to go from its full initial amount to half of that initial amount. So we have an equation, 1/2 a sub 0 equals a sub 0 times e to the k times 5,730. Solving for k, we can divide both sides by a sub 0. Then to undo an exponential function, we use logarithms. So we have the natural log of a half is equal to k times 5,730, which means k equals the natural log of a half divided by 5,730. And this is the exact answer for k. If we wanted to have a decimal approximation, it is about negative 0.00012,097. Notice that this is a negative number, which means that the graph of my radioactive decay is going to be decreasing from left to right. So here is a graph of the amount of carbon-14 in the object in terms of A sub naught. We weren't told exactly how much carbon-14 we had to start with. So the y-intercept is the point 0, A sub 0. And we also know the point 5,730 and then a half A sub 0. And we were able to solve for k. So now the question is, what fraction of the amount, of the initial amount, is there after 10,000 years? So we're going to plug in t equals 10,000. And the amount is A sub 0 times e raised to the negative 0.00012,097 times 10,000, which is e to the negative 1.2097, and that is approximately 0.298 times a sub 0. So just under 30% of the initial amount is there after 10,000 years. Another example is called logistic growth models. This is where the function f at t equals the fraction c divided by 1 plus a to the e bt, negative bt. C is called the carrying capacity or the limit. B is the constant determined by our growth rate. And the initial amount that we have is C over 1 plus A, and we'll see that. So we're going to do an example talking about the spread of the flu, of influenza. We know that F sub 0 equals 1. This is saying initially only one person has the flu. And we are also given that our population has 1,000 people in it. So the most number of people that could get sick is 1,000. So that's my carrying capacity. B is given to us as 0.6030. So that is how the flu is going to spread. 1, let's find the value of A. If I plug in t equals 0, then I get 1 equals 1,000 divided by 1 plus a e to the 0 power. But e to the 0 power just equals 1, so I have 1,000 over 1 plus a. Multiplying both sides by 1 plus a, we get 1 plus a equals 1,000, which means a equals 999. Question 2, how many people are predicted to be sick after sick with the flu after 10 days? So F at 10 equals 1,000 over 1 plus 999 e to the negative 6.030. That is b times t, negative b times t. And when I evaluate this in my calculator and round to the nearest person, we find that 294 people are sick. Our last example is talking about interest. So this might be interest for a savings account or for credit cards. The first formula that we have is A equals P times the quantity 1 plus R over N raised to the NT power. And this is calculating the interest when we compound the interest N times per year. So sometimes you hear things like the interest is calculated once a year, and that would be N equals 1. Or maybe they calculate the interest every month, which would be N equals 12, because that would be 12 times per year. P is the initial investment or principal. R is the annual interest rate. T is the time in years. And A is the current balance. Another way of doing interest is to compound continuously. So this is as n goes to infinity. And in that case, we use the equation A equals P e to the RT power. So one thing to remember or to feel confident about is that you get to write down these formulas in your notes and refer to them as you complete your homework. If you are doing one of these problems on a test, your professor will provide the formulas. You would be responsible for knowing what the variables represent. So let's do an example. Find the time required to grow an investment that started at $5,000 and we grow it to $6,200 at an interest rate of 7.5% compounded quarterly. So we are using the formula A equals P times 1 plus R over N to the NT power. 5,000 is my initial investment. It's growing to 6,200, so that's going to be the value of A. R is 7.5% or 0.075. And we are compounding quarterly, and there's 4 quarters in a year. So N equals 4. So we need to solve the equation for T. 6,200 equals 5,000 times 1 plus 0.075 over 4 raised to the 4t power. Going with order of operations, the first thing we're going to do is divide by 5,000. And so we get 6,200 divided by 5,000 is 1.24. And so now we have 1.24 equals 1.01875 raised to the 4t power. Exponential functions are undone by logarithms. So we're going to take the natural log of both sides. The reason I choose natural log is because our calculators have this button on it. You could also use log base 10, which is a button on our calculators. Now, using the properties of logarithms, I know that the natural log of 1.01875 raised to the 4t power is the same thing as 4 times t times natural log of 1.01875. I get to bring down the exponent. So solving for t, we're going to divide both sides by 4 natural log of 1.01875. And we find out that the time is about 2.89 years. So an initial investment of $5,000 at a 7.5% interest rate compounded quarterly will grow to $6,200 in only 2.89 years. And 2.89 years, if I take 0.89 times 12, that's actually almost 2 years and 11 months. About. It'll happen a little bit before that. And that is another model for using exponentials, using exponential functions.